Hey, this is Jeremy, and today we're going to be talking about tonicity. Now, tonicity is going to refer to the ability of a solution to cause the cell to gain or lose water, which is going to cause the cell to get larger or get smaller. And we can only refer to tonicity whenever we're talking about a comparison between two solutions. Now, in emergency medicine, the solutions that we're going to be talking about is going to be blood in the cells inside the body, and then whatever it is that we're putting into the body. So, for example, a hypotonic solution would be D5W, or dextrose 5% in water. That's a hypotonic solution. Normal saline is going to be an isotonic solution in comparison to the body. And a Hypertonic solution would be something like D50 or dextrose 50%. And that's going to be in relation to the body. So what we have is on the left side up here, we have inside the cell, and then on the right side we have outside the cell. So we have 3 solid molecules on each side, and we have 6 water molecules on each side. The thing about these molecules is, if you can just imagine throwing a whole bunch of bouncy balls into a hallway, that's how these molecules are reacting. You have sometimes they'll be traveling in this direction, sometimes they'll be traveling in that direction, and it's just kind of dependent on what it is that is going on. And this is all happening at the exact same time. It's happening on both sides. So you can have a water molecule that's going to leave, and then it's going to quickly be replaced by another water molecule. Okay, and this process is going to be dealing with osmosis, or the movement of solvents, because your water is going to be a solvent, and then your solids, those are going to be solutes. Now, so whenever we're talking about hypotonic versus isotonic versus hypertonic, this process right here in the center, the movement of the water molecules, is really what we're going to be referring to. So if I have a fluid that has, or let's say that my cells have significantly more solid particles in them than the outside of the cells do. So what this means is we have fluid that is going to be able to go into my cells a whole lot easier than I have water molecules on the inside of the cell that are going to be able to make it out. Because what's going to happen is these water molecules on the outside, they can go in unobstructed, but as the inside molecules, a lot of times they are getting obstructed by these solid particles. And so while you do have some that can exit the cell wall or the cell membrane, you're eventually going to have something called a net inflow. Okay, and so this is going to be what's happening to a hypotonic solution. Okay, these are going to be net inflow. Okay, and so what this means is that I have right here in the center, I have a typical red blood cell, and it has water molecules inside of it. And it also is going to have water molecules on the outside of it. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's also going to have solid particles on the inside of it and the outside of it. And everything is going to be able to move in between the cell membrane. It's going to be able to move freely. Now, if I have something over here, such as what's going to be in a hypotonic solution, where I have a lot of solid particles in relation to the fluid on the outside. So what happens is, as I have water molecules that are flowing inside through these cell membranes, I have a good bit more water molecules in relation to the solid particles outside the cell than I do inside the cell. And so what happens is I have a higher probability of water molecules going into my cell than I have water molecules leaving my cell. And so this is going to, again, result in that net inflow, and this is going to cause the cells to get larger. And a fluid that we are going to deal with that can cause this to happen is going to be D5W, or dextrose 5% dissolved in water. Okay, and this would be something that could be beneficial for some patients, such as patients who are suffering from a sickle cell crisis and things like that. So, so a hypotonic solution would be D5W, and it would cause the cells to get larger. And what that does is that can eventually lead to something called lysis. And so as the cell continues to grow, as it continues to get larger, because I have more water molecules that are floating inside, what happens is the cell is eventually going to hit a point where it has a leak. And that leak is going to essentially bust, just like you would expect out of a balloon that gets too much air put into it. You have too much fluid in here, and it's going to cause everything to kind of just leave that cell, because there's nowhere else for it to go, or there's nothing that's going to be containing it. Now, in these isotonic solutions, such as normal saline, what happens is I have just as high of a chance of a cell entering, or a water molecule entering my cell, as I do a water molecule leaving my cell. And again, these water molecules, they're just bouncing around, they're each moving in their own different direction. And you have some that can bounce off of other solid particles, but what we have is it's really going to be a no net. Okay, everything is staying neutral. So this is you're really not getting a whole lot of change in your cellular content, concentration wise, versus the water, which is a solvent, and your solids, which are the solutes. Now, whenever we have a hypertonic solution, what happens with these is we have a higher concentration of solid particles outside of the cell. And so what this does is this means that the solid particles that are inside the cell, they are less likely. With all of these solid particles that I have outside the cell, they are more likely to prevent fluid from entering the cell than vice versa. So what this means is this is going to cause my cell to end up actually losing some of its shape, because part of what actually gives the cell its shape is going to be the fluid that it's in, or the fluid that's contained within it, so these water molecules. And if these water molecules all eventually leave the cell, I have more water molecules leaving the cell than I have that's entering the cell, then it's going to cause a process called crenation, which is eventually going to essentially cause the cell to collapse in on itself. And this is actually where the damage from D50, as part of being a necrotic solution, whenever you have extravasation, wherever it enters the extravascular space. So what this results in is a net outflow, because I have more water molecules that are leaving the cell than I have that are entering the cell. Okay, so the big thing to take away from this is understand that whenever we're talking about hypotonic, isotonic, and hypertonic solutions in the context of emergency medicine, we're going to be talking about the comparison between the fluid that we're giving, such as normal saline, to the body cells, the body's blood content, and all that. And through that fluid, that isotonic, hypotonic, or hypertonic solution, I am either going to have a cell get larger and it's going to get rounder, or I'm going to have a cell get smaller and it's going to start losing its shape, or I can have a cell that stays the exact same. And it's all going to depend on what fluid you decide you're going to give your patients, whether it be D5, normal saline, D50, or whatever it is that you're giving your patient. It is going to cause a net inflow if it's a hypotonic solution. It's going to cause a net outflow if it's a hypertonic solution, and then everything's going to be really neutral if we have those isotonic solutions. So I hope that you're able to take away from this a little bit more of the foundational knowledge as far as how the cell membranes work and how the solutes and solvents work in relation to the cell membrane, and how tonicity fits into all that.